So, Joe, I need to introduce you formally to the audience. So, Professor Dr. Joseph Niemela, he is a fluid dynamics scientist in the field of fluid dynamics, experimentalist. I think particularly your main interest is in experiments, Joseph, as I, right? And you have had a group in ICTP also. And the previous director of ICTP was Dr. Srinivasan, and you have been working with him also. And his contribution in the area of popularization and helping younger researchers for promoting theoretical physics is tremendous. He has been associated with ICTP for the very long years, and he was head of the external affairs of ICTP. And he, supported the third world countries and developing countries to promote science and particularly theoretical physics. And he also helped the National Center for Physics in Pakistan and Pakistan Atomic Energy Commission. Many students availed opportunities to visit ICTP, and he was helpful in that case also. And he also started with the collaboration of Director of National Center for Physics for arranging joint activities of ICTP and NCP. That was very useful activities actually. And due to pandemic, I think there is a big gap. Maybe it can be started again, and I think comstech and ICTP will cooperate in future. And Professor Niemela is chair-elect of the Forum on International Physics of the American Physical Society, Secretary of Commission 13, Physics for Development of the International Union of Pure and Applied Physics, and chair of the Physics for Development Group of the European Physical Society. He is fellow of the American Physical Society, and he has several very important and good research papers on his credit. So I think now we request Professor Dr. Iqbal Chaudhry to say a few words.
Thank you very much, Dr. Saab. People like you, Professor Joseph Niemela, are not really, they don't belong to any country. They have this universal view. You are a global citizen. You are the one who every nation in the world can claim to be associated with. So your contributions are beyond institution and borders, and that is where we see a real worth of a person who really go beyond nationalities. And so this is where we feel that your contribution can be immensely beneficial, because me and Dr. Hamid Salim are actively discussing how we can promote basic sciences in the OIC countries. This committee of Standing Committee for Science and Technology, which is called comstech, is of 57 ministers of science and technology. So it's a very large organization, and it's spread in 4 different continents, from Suriname to Brunei Darussalam. This whole spectrum of countries, developed countries, underdeveloped countries, and least developed countries. But one thing which is of a generic nature is very weak basic sciences. And that is perhaps one important impediment which is stopping the development of real science or interdisciplinary science at the end of the day, because students have a very weak foundation of these sciences. And ICTP is certainly one example which has played a very important role in the development of physics in the world. And we would like comstech to become kind of a prototype of ICTP by including the other 2 disciplines, 3 disciplines: chemistry, biology, physics, and mathematics. So we would like this huge headquarters of ours in Islamabad to serve as a mini ICTP, as a place where we should have regular events organized to develop capacity in basic sciences. And that is what I actually dream for. For that, I would be looking forward to have your guidance and support. This is something which can help people to develop real capacity in science and technology, and especially in the OIC world, where we would like science and technology to become part of the culture. It is important that we inculcate these potential and these attributes in the younger people. And with this, I would like to thank you for your active support to us and welcome you to Comstech platform. We would be recording your lecture also, hopefully with your permission, and this would be available for the other people to watch. Thank you very much, Professor Niemela.
You're very welcome, Dr. Chaudhry. It's as you said, I've been at ICDP for long enough, and with the UNESCO system, that I really do feel, in a sense, like a global citizen, because I've kind of lost track of it, not really lost track of where I came from, but I just feel when you are in a wonderful place like ICDP and you travel around, you really get a sense that it's just one big community of fellow human beings, and that's also for developing science, which is one of those universal languages that I think we can all agree on. And I think what you said about basic sciences is very important. By the way, there is an international year which was just announced for basic sciences for sustainable development, and I think this is a great opportunity also to work with different sectors of society to really reinforce the importance of basic sciences for the country, for humanity, to solve some of our deepest crises in health and the climate and energy, et cetera. We really need the basic sciences, and this needs to be really a global endeavor, not just for some nations, for all nations, all people. So anyway, I share your feelings, and I'm really happy to help in any way I can through the platform here. Anyway, it's a great pleasure to be here at Comstech, and with my great friend Hamid Salim, because Hamid Salim actually introduced me to Pakistan. I had never been to Pakistan. And in fact, he was here at ICDP, and he said, the subject came up about the International Scientific Spring, which happened every spring in March, and where so many young people came from all over, from institutions around Pakistan. And it was a wonderful, really a wonderful opportunity. And we've been doing it ever since, except COVID, of course, has interrupted the physical presence the last couple of years. But I really thank Hamid for really introducing me to Pakistani culture, to Pakistani people, and to the science. And there's wonderful young people in science in Pakistan. I know that from firsthand experience. And some of them are here, and some of them are coming. They're still coming even now with the COVID. Occasionally we get a long-term visitor. So at any rate, I'm very thankful to my friend Hamid for that, and I'm really happy to be here. Thank you very much for the invitation.
Thank you.
So now you can start your formal lecture.
Okay. All right. So let me see if I can do this. I'll share the screen. Presumably I have that. Okay. And all right. So somebody stop me in case you don't see this. Nobody's stopping me, so I guess you do see it. All right. So yeah, let me take a drink of water first. Yeah, I'd like to, so this is a perspective of turbulent flows in both classical and quantum fluids. It's a little bit of an odd topic, and the fact that, flows in general, fluid flows, were often topics in the engineering courses, but rarely in physics courses, at least in the United States. But that's just a generality. And so I put a lot of pictures here on the opening slide. Let's see if my pointer, okay. So this is Professor Srinivasan, former director of ICDP that Hamid had mentioned. And Srini and I have been colleagues for many years on working on papers together in the area of turbulent flows. But really our background, I didn't start out life working in turbulence, fluid turbulence. And this is my advisor right here, so Russell Donnelly. And so really the story centers around this person because it's, you know, as we were just talking about, that, you know, often is one person that really unites or brings together different elements. And so his advisor was Lars Onsager at Yale. And Lars Onsager was somebody who had really identified what the flow looks like in a quantum fluid. And once he left Yale, he went to the University of Chicago, and then his colleague was Chandrasekhar, and he worked very closely with Chandrasekhar as a young assistant professor. And Chandrasekhar was also interested in classical flows, as in astrophysical flows, obviously, and also in quantum fluids, because, for instance, neutron stars behave very, very much like a superfluid. And so they had a great relationship. Joe Vinan, who is also a colleague of mine and a very good friend of Russell Donnelly, was the person who actually did what was the equivalent of a Millikan oil drop experiment with quantum fluids, with superfluid helium. He actually measured the quantum of circulation, and so that was his great claim to fame. And he's a wonderful person in this field. And then this person right over here on the right, that's Russ as an early young man. But the person in the middle is Sir J.I. Taylor, who was a great fluid mechanician. And so all of these people actually were involved together in trying to untangle what turbulent flows look like, not only in classical, but also in quantum fluids. So it's kind of a strange mixture. And there's a wonderful story surrounding this whole thing. So my own involvement, as Hamid mentioned, I'm an experimentalist. I'm working at the ICDP. I'm actually honestly retired from the ICDP, although I'm here as a consultant, and I remain here working with students. But I'm one of the few experimentalists here, and so that's what I do. And experimentally, I had started out as a low temperature physicist, working with liquid helium, mostly looking at static properties. But we eventually got this idea that we could really profit from the low temperature environment and from liquid helium itself to study fluid flows. Turbulence came much later. It seemed like too complicated of a problem, but it became something that Srinivasan and myself and with Russ really tackled. Okay, so I'll move on. So that's the background of the people involved. So turbulence itself is you can think of it as a paradigm problem for complex systems, something which for which the Nobel Prize in Physics was just awarded. And if you wanted to describe it, it's really strongly interacting and many temporal and spatial degrees of freedom. They really have to have the time element there, or it's not really turbulence. So it's temporal and spatial degrees of freedom. It's decidedly non-equilibrium, and the equations of motion are, of course, very nonlinear. So nonlinear that even though the equations of motion themselves are deterministic, it's not really possible to predict, looking at a small element of fluid, what it's knowing its velocity and position at one time, knowing what it'll be at another time, almost in principle, because of the nonlinearity. So it's a small change in those parameters can have huge effects. That's the so-called butterfly effect, or the sensitive dependence on initial conditions that really describes chaotic flows. And there's a sort of there's a limit to how precisely you can measure any of those things. So in some sense, it's not really possible for us to predict. And that's one of our problems, to predict really where any element of fluid will be at any later time. However, things that are very reproducible are the statistical measures of these complex systems like turbulence. And there's a strong tie between the dynamics that we're interested in and the statistics and the structure and the scaling properties that we see. So statistically, we have a chance to study turbulence and try to understand it a little bit better. For engineers, and it's very important for anything that's large, like airplanes, submarines, and I even showed it inertial confinement confusion, and that's touching on plasma people here, because there are many instabilities that arise that you need to understand. For engineers, it's not so much of an issue about understanding the turbulence as being able to control it, just from a practical point of view. And so things like wingtip vortices, you now see on all airplanes, you see the wings tend to flare up at the ends, and that's a way to limit those wingtip vortices. We still cannot model aircraft in full flight conditions. Still not possible with the computing power we have today, but we get pretty close. And then there's these sort of fixes that we make. And it's also, turbulence is found it's important in pollution dispersion in the atmosphere, in the oceans. And it's something that's present in many large-scale geophysical and astrophysical phenomena. And one of those would just be any star is really a very has a very turbulent characteristic to the flow in those stars, and the way they get energy out is through convection. That's at the outer edge of the star, and those are very turbulent flows. Even supernovas explosions have a very turbulent signature, and what you see here in this picture at the bottom right is actually a cartoon of a supernova explosion, which shows a kind of a Rayleigh-Taylor instability as a simulated feature. So at any rate, turbulence is everywhere. And in fact, going on to the next one, it's almost the rule in the flow of fluids. In fact, it's very difficult to make a flow, any reasonably large-scale flow, non-turbulent. You really have to work at it. So going back a few centuries, was Leonardo da Vinci, an engineer, well, I would say an Italian, but Italy didn't exist at that time. It was just a collection of city-states. But Leonardo da Vinci conducted what are considered the first recorded systematic investigations of turbulence. And this is one of his drawings in the middle here, and it shows water coming into a pool. Whoops, sorry about that. Water coming into a pool and flowing in and making a large scale, but also making many other scales of flow. And in his own words, he says the water has eddying motions, one part of which is due to the principal current, and the other to the random and reverse motion. The small eddies are almost numberless. That was actually a very accurate description. And in fact, he was very accurate in how he described not only these kind of flows, but the anatomy and everything else that he touched. So, and that's where we were back then, 5 centuries ago. 3 centuries later, Euler was sort of the father of the theory of fluids on circulating fluids. And he developed what are now called the Euler equations, which we'll get to. But he remarked that it's not really the laws of motion that we lack in order to pursue research in circulating fluids, but only the analysis, which has not been sufficiently developed for the purpose. That was back in the 18th century. More recently, Richard Feynman remarked on the same topic. He says, finally, there's a physical problem that is common to many fields, and nobody in physics has really been able to analyze it mathematically. That's the analysis of circulating and turbulent fluids. And Ken Wilson, who got the Nobel Prize related to renormalization group theory, in his Nobel lecture also remarked on turbulence, because that was one of his probably one of his inspirations in developing the renormalization group, was to actually study some complex flows like turbulence. And he said, really, it's defeated analytic techniques up till now. And that's where we are. Of course, it hasn't really evolved much since they said this. So we have a problem. It's because of the nonlinearity of the equations of motion. So what are they? So here the, well, there's Navier, there's Stokes, and here's a guy named Reynolds. All right, but these are the so-called Navier-Stokes equations. And they're partial differential equations. It's probably the only time I'm going to really throw one of these at you, but this term, the left-hand side is just the derivative of momentum with respect to time. And anybody that studies electrodynamics will recognize that it has a convective derivative. It's not only the u is the velocity. By the way, these are non-dimensional equations, so I'll get to that in a second, but it's not only the change in momentum for an element of fluid where it is, but that fluid also moves around because of the velocity and can go to a place where the velocity is different or the momentum is different. So that's a convective derivative. And for Euler, it was just related to the gradients in pressure. They caused, so if you have a low pressure, one example is here in Trieste, when we have the Bora, it creates a very low pressure outside and it sucks your windows out and they break on the sidewalk. But that's just the Euler equation. And then we have another term which actually takes into account shearing, strains and stresses in the fluid. And that was due to Navier and Stokes. And so this is a non-dimensional equation. In other words, we've taken everything, velocity, length scales, pressure, viscosity. We've normalized them by some factor to make this whole equation non-dimensional. So it applies to any flow, any fluid, no matter what flow it is. It could be hydrogen gas in a galaxy, or it could be the flow of water dripping from in your tub. So it's and so there's only one parameter in the entire equation. That's something we call the Reynolds number, and it modifies this last term. That's it. And this is every single flow in the universe can be described really, if you don't throw in relativistic effects, by this equation. And the Reynolds number is just the result of doing that normalization of all those variables. And it's a velocity, the large scale velocity times a large scale length scale, which is characteristic of the flow, divided by this thing called nu. It's the kinematic viscosity. It's really the shear viscosity divided by the density. But anyway, that's the velocity, it's viscosity, which is important for turbulent flows. And so this one parameter describes everything. Besides that, it's just initial conditions and boundary conditions. And so if you take flows which are similar, so here's a cylinder, just to illustrate it. You're looking down on a cylinder, the flow is going from left to right, and the cylinder is in the middle. If I was in person, I'd be using my hands a lot, and then you could maybe visualize this better. But the flow comes in from the left and it goes around the cylinder. That's pretty clear. It can't go through it. It's a solid cylinder. And then in the back, it has a back eddy, and then the flow converges again and then gets back to its general shape that it had coming in. And so that's a region. And here you really have only two. This is something at small Reynolds number 26. Let's say that's small. And you really have only two sizes. If you make it 2000, so you change the number here, it's just a number from 26 to 2000. This is what you get. Flow again comes in. This large scale doesn't really change much in its dimension, but you see there are many, many more scales, many small scales that have been added. And this is what happens with turbulence. And the turbulence occurs when Reynolds number is large, and that's how we define turbulence. Defined just by one number. You can compute this number for any flow that you have in mind, and you know right away if it's turbulent or it's non-turbulent just by the value of that Reynolds number. And all right, so that's just a primer on the equations of motion. The nonlinearity comes in here, and that's really what causes the complication. Just some dimensional considerations, because I'll make this easy, but this is typically what we do with anything we don't really understand. We look at time scales and try to understand things in terms of the relation of various time scales. So the molecular time scale, well, for diffusion of momentum, or diffusion of anything really, is the length scale divided by some kind of diffusivity, or in this case, a coefficient of viscosity, or it could be a coefficient of heat diffusivity. In this case, it's viscosity, so it's just L squared over nu. That's a time scale, and that's for things happening at a molecular level. So different molecules bouncing off each other, exchanging momentum. However, when you have a turbulent flow, things they also occur by molecular interaction, but much more efficiently they occur because there's a lot of flow going on, transporting elements of fluid from one place to another. And that the best time scale you can come up with is the length scale between two regions of interest and the velocity. And so that's a sort of a turbulent time scale. And if you compare those two, you end up with the Reynolds number. So that's the way to think of a Reynolds number. It's better for physicists to think in terms of time scales. And in this case, it's just interpreted as a ratio of molecular and turbulent time scales for diffusion of momentum or anything else you're interested in. And in that case, diffusion becomes much more enhanced with turbulence, and that's what we know. All right, so here's an interpretation. And this is all just a general introduction, because I'm moving towards some experiments, but I want to give you an idea how we think about turbulence when we can't really solve the equations of motion. And so here's an interpretation in line with the Richardson cascade. And he was a poet, as many of the British physicists or scientists over the years have been poets. It's actually a very common thing, and it's kind of a nice thing. And he mentioned that big whirls have little whirls that feed on the velocity, and little whirls have lesser whirls, and so on to viscosity. Well, what does that poem mean? It just means, and looking at this picture here, means that energy comes in at a large scale. And so these few eddies are large and contain all the energy. And that energy is converted, converted into, undergoes a cascade. And so the kinetic energy, the larger eddies, goes into creating slightly smaller ones, and so forth. It's a cascade process. And at the end, the eddies that, depending on the level of turbulence, or the Reynolds number, that's really dependent on the Reynolds number, the smallest scales, that kinetic energy is then converted into heat. And I'm going to describe how small those small scales are, because we can, again, with just back of the envelope calculations, you can determine that. And but that's the general idea. It's a cascade of energy. It's not, you can't take energy from a big scale and bring it all and have it converted into a very small scale. And there's a reason for that. One of the reasons is there's very little shear in big scales, whereas it's tremendous in the small scales. And the small scales can't interact much on the big scales, even though they have a lot of shear, because they aren't coherent over the large scale. So really they have to go scale to scale, and that's why it's called a cascade, not just a transfer of energy. And that's actually a very important consideration to understand turbulence, the idea that it's a cascade and not just a simple transfer of energy. All right, so how small are the smallest scales in a turbulent flow, you ask? So again, increasing Reynolds number simply allows this cascade to continue to smaller scales until viscosity dominates. And that small scale keeps getting smaller and smaller and smaller the more we make Reynolds larger. And so we can compute that. First, we need to actually understand what is the energy dissipation, always per unit mass, little epsilon. And we can calculate that we can compute that by calculating something that we actually have some chance of knowing, which is the rate at which kinetic energy is injected in the flow. And so that's just kinetic energy times the rate. And so you really get the velocity q divided by some length scale L, and that really is the energy dissipation rate. It has to be equal to the energy injection rate. There's no place where energy piles up or gets taken out in between. So, and then just as we just did, calculate 2 times. One is the turbulent time, which is whatever scale you're thinking about. I'll just call it little L, because it could be a small eddy, not necessarily the large scale. That length scale divided by velocity gives you something taken from this relation. And the molecular time scale is always, again, length scale squared divided by viscosity. And that's for that same little scale or big scale, doesn't matter. I'm just making it generalized. Now, if I set those 2 things equal, that's really the smallest scale, because that's where viscosity, where molecular action becomes dominant, and and molecular action describes that viscosity, which is turning this kinetic energy into heat. And so we can just solve all that only using these relations right here, and we get a relation between that depends on the viscosity and this dissipation rate, which I just defined. And that you can rearrange, and it looks like this. So the smallest scale is really dependent on the big scale times this Reynolds number to some power. And so now we know what the smallest scale, we can compute the smallest scale just knowing what the Reynolds number is. And again, here's this range, and you see the range goes like the Reynolds number to the 3/4 power, at least in 1 dimension. It goes like Reynolds number to the 9/4 in 3 dimensions. So the range it goes more than linearly, increases more than linearly with Reynolds number. And so here's a schematic, again, the same one from L to eta, but that doesn't really tell us much. It's just a picture. And it's hard to really think in terms of the physical scales. It's better to look in terms of wave number. And this is the ideas due to Kolmogorov. And now you know this is the heart of turbulence. And once you know this, you know just about everything. And so if we look at the spectrum of energy, looking at this picture, but converting the wave number, we see at 1/L, this is where the energy is really concentrated in those particular eddies of that size. And then it rolls off with a power law relationship until it gets down to the lowest, smallest scale. That's where it's now dissipated. This energy is dissipated into heat. And so this is the so-called inertial range, and it has this spectrum has some kind of relation that goes like the wave number to the -5/3. And if you only know one thing about turbulence, this is the one thing to know, that the energy spectrum rolls off like k to the -5/3, and now you know where it comes from. And so to look for universal properties, so in other words, now putting on the hat, not as an engineer, but as a physicist, we want to understand what is this thing that we call turbulence, which nobody has been able to analyze mathematically, yet is so important for so many problems. We want to really stretch Reynolds number, make it as big as possible. And the reason for that is that if we look in here and somewhere in this inertial range in the middle, because of the cascade process, it only sees eddies on around its neighborhood. Where am I going here? Okay, only around its neighborhood. So it doesn't see what we did to make the eddy make the turbulence in the first place, and it doesn't see this process where energy gets converted into heat. So it's, in other words, let Reynolds go to infinity. We stretch this region very far because we make 1/eta go way out here. So that having a large inertial range allows us to look for universal properties. And so this is what we're going to have to do experimentally. And by the way, it's not the same saying a Reynolds number is going to infinity is definitely not the same as saying it is infinity, because going to infinity implies that there is a scale at which viscosity acts. Reynolds number equal to infinity, there is no scale at which viscosity acts. And I'll just zip back in my talk to that equation here. And so that's, if Reynolds number is infinity, you could say, well, I can get rid of this term, 1 over infinity, right? And I end up with the Euler equation, which is much simpler. But Reynolds number going to infinity doesn't allow me to do that. And that's a typical mistake. Everybody that, any mathematician or anybody actually that comes and sees this equation immediately says, why don't you just, if you're going to worry about turbulence, Reynolds number is really high, really large number. This is really going to 0. So you just get rid of that term and solve, make the equation much easier. But the problem is that the gradient in velocity actually is increasing as well, and it's increasing very fast. And that's what when I said the small scales have the greatest shear, that's because of this term. And so you can never get rid of this term. The higher you make Reynolds number, the greater this term becomes. So it's just canceling out that effect. So at any rate, so we didn't get any, there was no advantage there. And the other problem I wanted to mention is the computer simulations suffer from the fact that the range of scales, as I said, go like Reynolds to the 9/4, and really we're beyond the capabilities of our computers even today. Maybe with quantum computing, true quantum computing, we might be a little bit closer. We're going to gain a few factors there, but who knows? Anyway, we're kind of stuck. We can only go so far with fully resolved simulations without making some approximations, and so a lot of the effort has been on experiments. So that's where Srinivas and myself and Russ Donnelly and others came in. We thought, why can't we go back to our favorite fluid, which is helium, and try to really experimentally get as far as we possibly can in increasing the Reynolds number, right? And so, and if we look at the Reynolds number again, it's the velocity times the length divided by a kinematic viscosity. So you can't really do much about the velocity, because if I make the velocity, if I start increasing the velocity too much in whatever apparatus I have, I'm going to start approaching the speed of sound, and that introduces another parameter. It's called the Mach number, and we don't want to do that. So we see there's a limit to how far you can push the velocity. The length scale, it's just a matter of technical convenience. Let's say you can't make things linearly, keep increasing them to enormous sizes. But we can actually play around with the viscosity by looking at other fluids. So it doesn't have to be water, it doesn't have to be air. It could be, for instance, helium, and helium has the lowest viscosity of any fluid that we know of. And in fact, we actually designed, where we started on this whole project was designing a superfluid wind tunnel. And we weren't the first. Feynman actually thought about this at Caltech, and it didn't get very far, but we took it a little bit further, and we're really going to push this. But that's a really expensive proposition. But a small wind tunnel like this, which could fit into the room that you're sitting in right now, was comparable to the NASA Ames tunnel, which is they actually put full-size jet aircraft in here. So it's it's a really saves on space because of the extremely small kinematic viscosity. And the other thing I want to mention is you could do experiments in the atmosphere, for instance, just instrument the atmosphere, because L is in fact very large. The problem there is you don't have controlled conditions. So if you really wanted to do things in a controlled way and understand them to answer very subtle questions, you really have to do experiments. And then again, you can't go into the atmosphere, you can't go in the oceans. You really have to do something in a laboratory. And then really your only chance is to find the fluid. One question you could ask is, what if we really push this thing to the limit and we produce scales so small they're comparable to the mean free path? Turns out that's not a problem at all, at least on paper, because the effective mean free path, it keeps on decreasing the more turbulent things become. That's actually a kind of an interesting exercise you can also do, but we won't do it here. All right, so that was the idea. So here's the phase diagram of helium. So pressure versus temperature. So this is temperature in Kelvin, so it's quite low. There's absolute zero down here. The first thing you notice, it's not a solid. That's because of its 0 point motion. But the helium has a critical point. There's a vapor phase which exists down. You can see where it is. There's a helium-1 is just it's a fluid. It's actually a very light fluid. The density is something like 0.12, but it's compared to water, which is 1 in CGS units. So it's a very light fluid. You might call it a heavy gas, but it is a liquid, and that's completely classical. But there's a transition here, which depends slightly on pressure, and that goes from something as a phase transition from a classical fluid to a quantum fluid. So the quantum fluid is on this side, and that has very unusual properties. I'm not going to go into a lot of details, but it has its own velocity fields and densities. It has the superfluid. It's sort of a mixture of a superfluid and a normal fluid, and these are really excitations in the fluid. It's defined by having the de Broglie wavelength larger than the interatomic distance. If you're familiar with Bose-Einstein condensation, this is a manifestation of Bose-Einstein condensation, except that it's a liquid, not a gas, not a perfect gas. So it's an interacting Bose-Einstein condensed fluid. So it's a little bit different. And even at absolute zero, only 14% of the atoms are really condensed into that zero momentum state. So at any rate, that's where it is. So you can describe this in terms of macroscopic wave functions. And these are really nonlinear Schrodinger equation, which has a phase, which is the function of position. And the velocity is just is related to the gradient of the phase. And h here is Planck's constant divided by the mass of a single helium atom. And the thing that you'll notice about this velocity, this is the velocity in the quantum fluid, not in the classical. So purely quantum mechanical, but the thing you'll notice, if you take the curl of that, it goes to zero, which really means there's no possibility of having turbulence or circulation. And but what we know is that actually there's a finite circulation around a singularity, a line singularity, which is a hollow vortex core. That core is about the size of it's about an angstrom in size. So the core is actually smaller than the atomic dimension. This was actually something, this whole picture about having a vortex with such a small core and allowing you to have flow even though the curl is zero is something that came about from Onsager. 6 years before Feynman actually went through this exercise. Much to Feynman's shock, actually, he said, "Wow, I saw it as a footnote in one of Onsager's papers 6 years ago, in which he solved everything. He just stated as a matter of fact everything that in this paper I've just showed you." So it, but the point is, you can take a line integral and as long as, and it should be the same as an area integral, which would be zero, except that you can't shrink it down because there's a hollow vortex core. And so when you do that integral of this velocity around the vortex, you just get the change of phase times h over m, the mass of the helium. And that change of phase has to be a multiple of 2 pi. And then Feynman theorized that, well, okay, so it's probably turbulence will exist as a tangle of singly quantized vortex filaments. Otherwise, it's a really strange fluid. It only has one kind of circulation that's quantized in terms of H over M. What Vinan did was to actually measure that, and he found that N was equal to 1. It was never really equal to 2 or 3 or 4 or anything else. And so these were energetically favorable that it would be singly quantized. And so this is what I said, sort of the Millikan oil drop experiment for liquid helium. So anyway, so here's some pictures. I'll just go quickly. We know these vortices exist. How do we know it? Each one of these things, this is actually Nobel Prize worthy work, although it was never awarded. But the way that Yarmchuk, this was actually Dick Packard's group, did it was to rotate a bucket of helium. And when you rotate a bucket, the superfluid is a very low temperature, so it's really helium-2, really the superfluid part. When you rotate it, you still get a meniscus, which was completely wasn't understood at all, actually, because it should have zero, the viscosity should be going to 0, really, and it should just, the bucket should rotate around the fluid, not entrain it. And so, but what happens is it starts getting populated by vortices, and the vortices have some kind of energy per unit length. They pull down on the surface, you get a meniscus. You actually do get solid body rotation because of the quantized vortices. The way you see them as an experimentalist, of course, to me, that's the interesting part, is they bombarded the vortex lines with ions. The ions, which are just ionic helium, the ions get trapped on the cores, and then from above, you apply an electric field and you suck up the ions along the core and have them expose a photographic plate. And that's what you're looking at here on these pictures, a photographic plate showing the bright spots or where the ions are contacting that photographic plate. And so you see there's an array at low rotation rates. You have one vortex in the middle, and at high rotation rates, you have many. So that was a wonderful work, but it's indirect. It's indirectly showing you have quantized vortices. This might be what a turbulent tangle would look like, except it's too random. And in fact, if we try to think about things that are producing classical turbulence, we need to have vortices bundling up together and partially polarizing bundles, which can mimic all different scales. Because again, in classical Kolmogorov turbulence, there's every scale. From the large scale to the small scale. It can't just be one scale of the singly quantized vortices. And in fact, that scale, the only thing that you have with a random tangle like that is just the intervortex line spacing. So that can't possibly be classical. And in fact, there was an experiment, and that was as recently as 1998. And this is a superfluid washing machine. So there are two discs that rotated in opposite directions, one at the top and one at the bottom. That just created, it's like a washing machine. It created a lot of turbulence. And what Moore and Tabeling did was measure the pressure. And so they're able to calculate the energy as a function of frequency, which is essentially the Kolmogorov relationship, and in the time domain rather than the spatial domain. And they found minus 5/3 roll off in this inertial range, entirely classical. Well, that's okay for helium-1, but they also did it for helium. Oops, there's a mistake there. That should be C, B, and C. But they also did it for helium-2, where it's almost entirely superfluid, and so really it should not look classical. Yet they all look identical. And so why was that? And we have a lot of reasons to believe, we actually know why that is, because they really do couple together through something called mutual friction. But at any rate, you still have classical turbulence, even in a quantum fluid. It looks exactly the same. But what about at t equals 0? So we can't really do that experimentally. We can get close, but it's always a question of how close is that. But let's just suppose you went to T equals 0 where there is no viscosity. Oops, where would the turbulent energy go without viscosity? So here I come back to this pictorial representation. So the energy comes in at some big scale, whatever that is. Maybe we pulled a grid or we flap something to make some turbulent motion, or that's the washing machine discs moving. But that's where the energy is getting injected into the flow. There's an energy flow, a classical one, which we know even happens in the turbulent fluid. And but at T equals 0, it doesn't go to viscosity, it doesn't go to heat. Where does it go? Well, what we believe is it goes to oscillations on the cores of the vortex. And so it's not a connection of bundles of vortices. It's actually instabilities on the vortex core itself. These are helical waves which are excited. And the way to understand that is to think about what happens when two line vortices come together. Here's one, and here's another one. What happens is they reconnect. So this vortex takes a piece of the other vortex, and like this vortex takes a piece of that vortex. And here's the short time later, then they move apart. Now you have a new vortex, but each vortex has a kink in it. And this is just like plucking a string on a guitar. So that kink relaxes. And just as in a guitar, it relaxes and there's a wave motion along the string or along the core in this case. And that's where we think the energy goes. It goes into making sound or phonons. So it's really a classical Richardson cascade on large scales. And then you have this sort of Kelvin wave, so-called Kelvin wave cascade on scales less than the intervortex line spacing, and all the energy goes into phonons. And that's really where we're aiming now with experiments. The difficulty is trying to do experiments at, say, millikelvin temperatures. It's really difficult to do it, like, say, a turbulent experiment, and not lose control of the heating, and also to be able to measure these kind of effects. So, but anyway, that's the picture we have. And if we looked at this, I showed you this earlier, but I didn't comment on it. These are simulations of a tangle of vortices, and this is T much greater than 0, and this is T, but still quantized, and this is T equal to 0. And you'll see that the T equals 0 is really crinkly, and this is really smooth. And that's it. I mentioned in passing this mutual friction between a normal and a superfluid component. That smooths out all this, so you don't really see this reconnection business so much at higher temperatures, but you do as the temperature goes down, and you start seeing kinks in the vortices. So can you measure that? Well, turns out until 2006, nobody had ever visualized a quantized vortex. I showed you pictures, indirect evidence, where they attracted ions to the vortex core and then drew them up vertically and exposed a photographic plate. But that was just an indirect representation of the existence of vortices. What Bewley did, this is Greg Bewley, who was at Yale, later went to Maryland with Srinivas and Matt Poletti. But it was really something started by Bewley. It actually started in our lab at the University of Oregon with this apparatus. And the idea was just to create vortices and to visualize them with hydrogen. Now, people have been doing that for many years. They really threw hydrogen at the flow. But what happened is it made big clumps and it all fell at the bottom. You were able to visualize some big flows, but you couldn't see anything like a vortex because the hydrogen clumps were too big. And what Bewley did, it's really so simple when you think about it, but nobody had ever done it before. He really found a way to, using fluidized beds, to get the hydrogen to make it so dilute that it didn't clump up. And he was able to actually visualize vortices. So here's something at this picture right here on the top left is just helium-1. That's a classical fluid. There are no vortex lines because they don't exist. And here in the middle is something below the transition to the quantum fluid state. But here on the right is when Bewley actually applied rotation. And so we know, and there's actually a Feynman rule, it tells you how many vortices and what their shape is when you rotate a fluid that in order to simulate this solid body rotation. And so Bewley simply rotated the whole apparatus and was able to produce a rectilinear array of quantized vortices visualized because all this hydrogen stuck on them, and he used sort of particle image velocimetry, but he's really just shining a laser sheet in and then looking at it with a camera at right angles. So those were the vortices. That's the first picture, and this appeared in his Nature article, the first picture ever of quantized vortices. But more than that, they actually saw, here's two vortices coming together, crossing and forming a pair of reconnected vortices which fly apart. And if you want to really get, you can read this PRL here, and then I wrote a nice, as more of a tutorial, was a way to explain what the PRL was talking about. That's with the physics.aps.org. And so this is actually the first volume, but it was all about reconnections. And I wrote it for the non-specialist as opposed to the PRL, which is really going to a specialized audience. And that was the idea that the American Physical Society had. And so if you want to understand a little bit about this really groundbreaking work, I would start maybe with this article, which brings it in a little bit more gentle terms. All right, so anyway, that's where we were. The other question is, we talked about polarized bundles. If we made them, would they coherently reconnect? And that's another fantastic simulation done by Carlo Barangi and his group. In fact, here's a bundle of a parallel bundle of vortices, two of them. They're made to interact, and they in fact do reconnect coherently. So we even know from simulations, at least, that this can happen. All right, so the last thing I'm going to talk about very briefly, that was all quantum flows, and really the message there was that classical turbulence exists in a quantum fluid, just like it does in the classical fluid, but there are restrictions to the quantized nature of the circulation. And as you go to t equals 0, these restrictions become more and more important. Now what I want to talk about are entirely classical turbulent flows. And again, just brief, I'll just talk about convective flows because most large-scale turbulent flows in nature are buoyancy driven. And that's because in every normal star like our sun, there's a core, sort of where fusion is taking place. It's that the energy is radiated outwards, but in the last 1/3 of the radius of the star, that's a convective zone. It's just like a pot of water boiling on your stove, maybe not boiling, but that's a convective zone, and heat is taken out through convective motions. There's also convective motions everywhere. There's convective motion underneath the surface of the Earth, the crust, and that's what's leading to plate tectonics. That's not turbulent. It's very viscous. But where you do see turbulence is in the outer core. That is a highly turbulent flow of in that outer core, which is fluid, not the inner core, which is a solid. And that's what gives rise to our magnetic field. And the turbulence actually is important because it does reverse. And that's also a source of a number of experiments using liquid sodium recently to try to understand that dynamo effect by which you generate the magnetic field in the first place through turbulent motions, but also have it spontaneously reverse itself. And that has happened all through the Earth's history. And you see that by looking at lava flows, because when the lava condenses and solidifies, it actually freezes in the direction, because it has iron in it. It freezes in the direction of the magnetic field which is prevailing at the time. And so we know that periodically, say over 500,000 years, it's not periodic, by the way, but let's say every few 100,000 years, the magnetic field will reverse. What happens when it's reversing is actually kind of interesting, because that's probably when you have a lot of mutations happening, because the magnetic field is what protects us from the cosmic rays. So there's a period which probably isn't large on a geological time scale, but it's certainly large on a human time scale when there's no magnetic field. And that actually can be very dangerous for creatures living on the Earth. All right. So anyway, so let's talk about convection. And the idea is to really try to understand what's happening in stars. And the simplified version of this is, rather than build a star, which I know the plasma physicists would love to do, but rather than try to do that in a laboratory, we try to think of a very simplified problem, which is called Rayleigh-Benard convection. It's really just a slab of fluid which has an expansion coefficient. It expands when it's heated, or vice versa. Viscosity, you already saw kinematic viscosity and diffusivity, and you heat it from below and cool from above in the usual case, and you get convective motions. And really, there's only one parameter that matters. It's called the Rayleigh number. That's G is gravity and alpha is expansion coefficient. There's a gradient in temperature. There's a height, H, the fluid level, and those two diffusivities. That's it. It's non-dimensional. That describes the state of the fluid. There are other dynamical parameters, but there's nothing as important as the Rayleigh number that really tells us where we are, just like the Reynolds number. The Rayleigh number is actually related to the Reynolds number as well for these flows, but it is for thermally convecting flows, the equivalent of the Reynolds number. And so turbulent flows have a high Rayleigh number. So that's all you actually need to know. You need to get high Rayleigh number, just like we were thinking we needed to get high Reynolds number. And here's the sort of a schematic. You see a person, just body heat will generate convection, which is already turbulent. You don't see it, but if you could visualize your own self, you would see turbulent flow from the heat emitting from your body, and that's around 10 to the 6th. At 10 to the 21, you have the sun, and so it's really measured on a logarithmic scale. And so this is the sort of the range of turbulence from 10 to the 6th to the largest one we know of is our sun, which is around, we estimate around 10 to the 21 for that value of the Rayleigh number. So the question is, can we get anywhere close to that? Because that's really something very fundamental and interesting. And one thing we can measure is sort of the global heat transfer. That's something that it's sort of the Thevenin equivalent measurement. That's if you had a black box and you knew how much heat you put in and you measured how much heat came out, that would tell you something about. You wouldn't have to know all the moving parts inside, but it would tell you how efficient it was. And this Nusselt number is the actual heat flux divided by some heat flux just for conduction at the same temperature difference. So but what it really is an ratio of effective thermal conductivity to the conductive value. And so it just means that when you make things really turbulent, the turbulent thermal conductivity gets very large. And what we know is that it has a power law relationship with the Rayleigh number, with some power beta, as Rayleigh tends to infinity. What we'd really like to know is what that is for the sun, because the way the sun is analyzed, or other stars, is through models, and they typically have some kind of relation like this, and they have various values of beta, but there are two values. There's a classical value of 1/3, and then there's a value of 1/2. It can't be bigger than 1/2. It could be a little bit smaller than 1/3, but this is really the high Rayleigh number limits, and 1/3 assumes some molecular transport in diffusive boundary layers, and 1/2 just assumes it's all turbulent. All right, but that's a big question. And so the idea we had, could we design an experiment where we could distinguish between those two exponents? That also could have been very, it's actually an important experiment. because you can really touch on what's going on in something you can't measure anything in. And so the idea here was to get to 10 to the 21. And so if you want to see something, an interesting story, next year, if anybody reads the annual reviews of condensed matter physics, Srinivasan and myself wrote a biography of Russ Donnelly and this whole story about doing this, which is really the story where I came into studying turbulence. But it all goes back to Waxahachie, Texas, which is where the superconducting supercollider, which by the way was much bigger and much more powerful than the LHC is, but it never came to fruition because the U.S. Congress pulled the plug on it halfway through. But they still had some equipment, some refrigeration stations. And we thought, well, we want to make a huge experiment. So the bottom picture is our experiments. It's as tall as a 5-story building. And it's just to measure the thermal conductivity of the helium under turbulent conditions and see if we can see what happens as we get towards close to the Rayleigh number of the sun. Well, unfortunately, the SSC folded. The Department of Energy pulled out completely, but the National Science Foundation still approved the development of a large prototype just in case things turned around, because there was still Brookhaven and there's still CERN. And so anyway, that's actually existing. It's up here in Trieste. This is it. There's Marcelin Assoon, one of my graduate students in the background. So you see it's actually large. Most low temperature experiments are about 1 centimeter. No, the actual fluid part is about 1 centimeter. This is the convective cell, and it's 1 meter in height. Here it is. It's kind of blurry because it's spinning, and so we were able to rotate it as well. And we had to build a big pit in the floor in order to be able to take it out in a finite space we had. So at any rate, how does it work? Well, just briefly, we work in this pink area. If we look at the Rayleigh number, we're down here. This combination of fluid parameters, gravity is always the same, delta T is the same, H is the same, so those don't vary. The only thing that varies are the fluid parameters. And so this combination of expansion coefficient and viscosity and thermal diffusivity could be 10 to the minus 3 right here, or it could be 10 to the 9 right here. And by comparison with water, it's more or less constant at 10 or 0.1. So nowhere near 10 to the 9. So we could get a billion times better, higher Rayleigh number using helium than we can using water. And so that was a huge advantage. And since we're all low temperature physicists, we thought, well, why not? We can, in principle, get 12 orders of magnitude in the control parameter. And because scaling, as I said, is so important, that means all 12 orders of magnitude of that control parameter, the Rayleigh number, are in the turbulent regime. And we produce this up to the highest values ever attained, and it's still the highest value. And there's just a picture of what's going on. This is due to Leo Kadanoff. It's really a bunch of plumes, which are, you don't see them, but the birds are flying on plumes all the time. Plumes are what happen at high Rayleigh numbers. It's not a nice cellular structure. It's just these explosions, but they do work together and they make kind of a machine. And Kadanoff explained this. It's actually, the diagram is not exactly right, but it's close enough. And it's just a machine with no real moving parts except the plumes go up and they come down. All right, and all the different scales that are involved. But if you just measure the Nusselt number, the global heat transfer, you don't care it doesn't matter what's in there. That tends to be that's a statistical measure, which is pretty much invariant. All right, so what do we get? Here's the last thing, really. We measured that Nusselt number, and that's as a function of the Rayleigh number. It's just a straight line. It's the most boring plot in the world. It's a straight line. There's nothing more boring than a straight line. But what's not quite so boring is the fact that if you look at the conductivity enhancement, by making it turbulent, we've increased conductivity by a factor of 20,000 in this one experiment. And the other thing is, because we have all those orders of magnitude, we get a pretty good handle on the scaling exponent. And with all the corrections we can apply, that's 0.32, which is pretty close to 1/3. So in other words, even when we got up to 10 to the 17, which is getting up pretty close to what solar convection would have, we still haven't seen anything looking like 1/2. And so those are in these papers down here. And so that's where we were. And the very last thing I'm going to mention is this. You know, we can look at the advection diffusion equation. I'm just going to go through this really briefly, but we can calculate what the vertical heat flux ought to be. And, you know, rho is a density, C is a specific heat. And this is the conductive part. It's the molecular action. It's just molecular thermal diffusivity times the gradient and temperature. That's what tells you what the heat transfer is. And this is just Fourier's law. But with turbulence, you have this correlation of fluctuations in temperature theta and fluctuations in velocity U3. And that correlation is also in here. And let's do something that's absolutely wrong. It's just the wrong thing to think about, because turbulence is not a fluid. Turbulence is a flow. There is no turbulent fluid, but let's pretend there is. And if there is a turbulent fluid, anything we put in parentheses has the same units. We might as well make it look the same. We'll just call it something related to the gradient and temperature, but we'll say it's a turbulent diffusivity. And we'll just stick this thing right in here. And then we can solve for Nusselt number. And we find that the Nusselt number is actually is the ratio of the normalized value of effective thermal diffusivity, where kappa here is just a molecular diffusivity. And this effective one is exactly what you think. It's the turbulent one, turbulent diffusivity plus a molecular one, because both things act. So that's great. So now we have a little prediction with this. It's a little bit more than what's on here. You have to go through some steps, but at any rate, we have a prediction. But the question is, could you ever measure an effective diffusivity of a turbulent flow? Nobody's ever done it. And so we thought, well, first let's start and think about, you can think about a fluid, but you might as well think about a solid too, because you're not going to consider its motion. You're just going to consider that whatever that turbulent flow is, it's actually a fluid with a very complex diffusivity. And the way you measure complex diffusivities in anything like a rock, take a rock from the interior of the earth, you don't know if there's many different elements in that rock. It's not just one type of mineral or element. And so you may not know what the diffusivity is, but you could measure it. And the way you measure this is by oscillating the temperature. You cut a slab of material, and that's two flat plate faces, and you actually put an oscillating temperature, and then you measure the temperature someplace higher, some distance away from where you applied it. And this is a schematic, so don't take it too seriously, but the temperature here is oscillating like this. And as it goes into the fluid, the oscillation, the frequency stays the same, but the oscillation amplitude goes way down. It's a damping effect. And if you have a little sensor here and maybe one here, you can measure this damping of the oscillation. And so you take that over. And to get just the effect of the oscillation, you do a Fourier transform. So you take a time series anywhere in some position that you know, and look at the Fourier transform, the amplitude transform, not the power, and you'll see you have a couple of peaks. This is in the center. This is the side. Let's forget about the center. Consider the side. This is you can read that top point. That's just the temperature at that point. And it's the same, it's related to the temperature at the surface where you applied it, multiplied by some exponentially damping coefficient. And that exponential has this so-called Stokes layer, penetration depth, whatever you want to call it. And that's related to this effective diffusivity, whatever it is, you don't even have to be able to know what that is. Theoretically, it's just something that exists with the diffusivity. It acts like a diffusivity divided by the frequency of the oscillation. So, well, since you know everything, you know what the temperature is here, you know what the frequency is here, you know what the height is here. You have everything in here except this, and so you can solve for it. And when you do, you can actually calculate that ratio like we just calculated on the slide before. And in fact, lo and behold, it just gives you back the Nusselt number, which is what this really tells you, and that appeared in this article. What it tells you is that that this actually, you can measure the diffusivity, and it does look like you can actually pretend like it's a solid, even not even a fluid, and you can do that and still get an answer that makes sense. And we did this for a number of different conditions. It works perfectly. It doesn't work perfectly at much higher Rayleigh number. That's a number. That's something we have to get back to. And the one thing I want to mention is you can only do this at low temperature. You cannot possibly do this experiment at room temperature. And most, let's say 99.9% of all experiments on Earth that look at convection cannot possibly do this because they can't wiggle enough to at least to reproduce this experiment. What we did at low temperature, there's the heat capacity actually goes to 0, and so you can wiggle as much as you like. And so anyway, that allowed us to do this, and we haven't got back to it since. But anyway, that's where we are. But I think the main point is that, you know, experimentally we've gotten beyond where we can get to with simulations. What we do with simulations is we work to try to understand what the flows look like, and that helps us when we place sensors. For us, it's more numerical experiments than just the simulation. We try to mimic what we might do if we actually had an experiment, and that's an experimentalist point of view on simulation. Nobody's expecting that the analytical techniques will improve anytime soon, but simulations will, because computing continues to become more powerful. And again, once we have, and we're fast approaching having true quantum computers, that probably will allow us to get much further, and we'll be able to ask more detailed questions. Okay, so that's everything. And with that, I hope you followed a little bit. Again, like I say, turbulence is not a typical topic, but it's the only one I ever talk about in Pakistan. All right, so anyway, with that, here's my life as a dancer in Islamabad. And thanks a lot for your attention. And I'll stop the share.
So thank you very much. Questions?
Is there Q&A?
The rooms have questions here. Online.
Online.
Rooms से check करने questions.
I see one question. What happens if we decrease the Reynolds? Okay, let me see if that's the first question. Well, okay, if you decrease the Reynolds number, you get what we would call a laminar flow. So all the way down to 1, it's just it's a regular flow. It's not. It could even be non-time varying. So time variation comes in as Reynolds number increases more and more. Probably, I showed that first photograph of a flow by a cylinder, but generally around 40 or so, something like that, some number of tens of Reynolds number. This is where you start getting interesting circulations. Much below that, it's just the smallest you get is that absolutely there's no flow at all. but small Reynolds number flows are very laminar, they're very regular. These are things you'd like to also be able to control for a number of reasons. But again, for engineers, I mean, if you look at it on a plane's wing, you'll see lots of things, vortex generators, and they're little, look like razor blades out there, and a lot of different objects sitting on a wing. Those are just the best guesses of the engineers of Boeing or Airbus on how to deal with turbulent boundary layers and also wingtip vortices. But anyway, yeah. So it gets from a physicist point of view, it gets more interesting at low Reynolds number. I think my postdoctoral mentor at Santa Barbara talked about turbulence when back in those days, late 80s. And he says, well, you know, this is really uninteresting, you know, because we can't really do anything. It's, you know, if you can't linearize something, it's hard to get a handle on it. And that's, so anyway, he said, this is completely interesting, but if anybody wants to go, you know, be my guest, but don't expect me to follow. The funny thing is, he later became one of the proponents of turbulence studies. So everybody falls on it. It's like a disease. You can't stay away from it because it keeps eluding you, and you just want to do it. And it's more or less like my son is actually a professional, was a professional magician, and he played number games. He really worked with some of the top magicians around the world, and his favorite audience were mathematicians and physicists because they could not understand how he did what he did, and that they just fell into his trap. Turbulence is like that. The more you can't understand, the more you keep guessing, which is why you attract guys like Feynman. All right, so let me see if I see any.
Yes.
Yeah, you can estimate turbulent velocities. Yeah, there's a lot of scaling relations in the same way I was showing before. So the velocities scale with the size and of the eddies. The eddies, by the way, I showed as little circular, little circulations. I mean, that's just a representation. What an eddy, and that's an old English term, but what an eddy really refers to is just a correlation of velocity, with a particular velocity over a certain length scale. And if you had something circulating around and around and around like a vortex, that's a correlation between the velocity and that whole extent of it. So anyway, otherwise it gets a little dangerous to make. Let's see. Maximum moisture content, which reduction in water content will not cause an increase. I'm not sure I understand that question. It's about water content in soil. Yeah, I don't know. I'm not the expert on soil physics, but I do have an interesting story about soil physics. It goes back to Abdus Salam, who somebody came, and ICDB had a college on soil physics for a long time. And it's a very interesting topic and a very important one, but rumors have it, I wasn't around at the time. I actually never met Abdus Salam. Unfortunately, I came after his death, but rumors have it that he actually understood solar physics, and we started that. And he said, "Okay, go ahead." But anyway, we did it for a long time, and it was just as well. All right. So, would you like to define superfluid in the context of dissipation? Well, superfluids. Okay, so the superfluid is the question is defining superfluid in the context of dissipation, absolute temperature, as well as fluid velocity. Yeah, I don't know if it meant superfluid turbulence, but I could say a few things about the superfluid itself. One thing we know, and I didn't touch on it here, but now I have a chance, so I'll do it. There is no viscosity of the superfluid component, but there is an effective viscosity. There's no fluid, there's no shear viscosity. It simply does not, the superfluid component does not carry entropy. It has no viscosity. It's a rather superfluid. That's why it's called a superfluid. But when you make it turbulent, because of the quantized vortices, you do get in the friction between excitations from the normal fluid and those quantized vortices. That's the mutual friction. You do get an effective viscosity, kinematic viscosity, same units. And that effective kinematic viscosity, actually, the interesting thing is it's the, when you measure it, and we can measure it, and in fact, I've done that measurement myself. When you measure it, it looks exactly as you might have predicted using the normal fluid shear viscosity and the total density. That's a complete coincidence. The fact is that Joe Vinan and I wrote a review article, and we actually have a model in there for what the superfluid effective viscosity actually is. It's related to the quantum of circulation and has nothing to do with fluid properties at all. However, the quantum of circulation kappa, that H over m, Planck's constant over the mass of the helium atom, has the same units as viscosity, kinematic viscosity, centimeters squared per second. And it turns out it has the same size within a factor of 2, same value, numerical value. So it's a numerical coincidence. And so, you know, it threw us off for years thinking that we were actually measuring this thing we thought we were measuring, which is a fluid property of say, just the normal component, when in fact it was something completely quantum. And it was only when we refined the experiments that we found this. So at any rate, yeah. But you can, but the other thing about turbulence, the difference between turbulence and, let's say, chaotic flows, is turbulence is highly dissipative. If you turn off the energy, the turbulence won't remain. It dissipates extremely fast. So dissipation is a key element of defining turbulence as opposed to other kinds of flows. And so you have to keep pumping energy into a turbulent flow to keep it going. And you can see this right away. So anyway, that's a defining characteristic. Absolute temperature, well, absolute temperature matters because you really have to get that Bose-Einstein condensation occurring and really get that de Broglie wavelength small enough. So anyway, that's so absolute temperature really does matter. And dissipation is always important. And that's why it was so important, so interesting to consider what happens at zero temperature with turbulence. All right. Yep.
Can I ask
Sure.
one question?
Mhm.
So first of all, I would like to thank you for this nice, interesting, and illuminating talk about turbulence. So my question is, as it appears from your talk that we have now better understood the turbulence. Is there any chance for chaos to occur? Still, is there any chance for chaos to occur?
Yeah, absolutely. So chaos is a rather subset of the march towards turbulence. So it's a little bit more controlled. Turbulence is highly dissipative, as I said, so that's a big difference. It's in a different limit at very high Reynolds numbers or Rayleigh numbers, whichever. But you still find chaotic flows. That's for sure, absolutely. Any experiment working towards turbulence, fully developed turbulence, is undergoing chaotic regimes on the way there. But it's a slightly more controlled environment and much less dissipated. Dissipation is not a key factor there. So yeah, you do see that. We do actually, one of the reasons to study quantum fluids, we didn't just do it because they're quantum, but that was enough for some of us. But one of the questions, one of the ideas that that was in our minds was that if we really did not have a great handle on what does turbulence mean in terms of Navier-Stokes, what if we went to a pure quantum fluid, which has a different set of equations, by the way. Navier-Stokes. And it's in some sense simpler. In fact, the equations of motion for a quantum fluid, like superfluid helium, are really the Euler equations, but not just the Euler equations. You would think they would be the Euler equations only because of the lack of viscosity, but there's still a quantum stress term, which is added on, which looks like the other term we looked at with multiplied by 1 over Reynolds number in Navier-Stokes. So it still looks like Navier-Stokes. It's just a different, it's coming from the nonlinear Schrodinger equation. That's what it is. But it, in some sense, is a little simpler. That viscosity, that stress term only acts very close to the vortex cores. In fact, Feynman just said it off the top of his head that there's no reason to believe that turbulence in a quantum fluid would be any different than turbulence in a normal fluid. Although I don't know based on what, because there were no experiments at that time, unless you got very close to the core size. But at any rate, but our thought was, if we look at a different system, sometimes that helps. Look at another system which goes turbulent, which has slightly different conditions or maybe simpler equations, and compare. And through the comparison, can you find some insights? Because what we need are, brute force is probably not going to get us where we're going. I think probably in plasma and in other areas, there are situations where brute force calculations don't get you over the hump. You really need some sort of insight and some new direction, some eureka moment, in which will propel you further along. And I think that's what we're kind of looking for, and not necessarily found it, but anyway, that was the idea behind looking in quantum fluids as well as classical fluids, just to be able to compare and try to find commonalities and where there are differences to try to understand and see if we understand something about turbulence itself.
Another question. Can we relate the turbulence with the multivaluedness of the solution? Is there any connection, multivaluedness with turbulence?
Well, the multivaluedness of what? Because that's
of you.
Oh, okay. Yeah. All right. So right. Okay, good. So there are a number of, so one of the techniques, and I did it actually, it was in my talk. I didn't describe it. If I was only going to talk about that in a lecture series, I would go much more in depth. But that's the decomposition. And in fact, sometimes it's easier to think in terms of a mean flow and then fluctuations about the flow, and to treat those separately and then average over the fluctuations, say, and to try to get some better handle. I think our problem is it's something called the closure problem for turbulent flows. Is you never match up the number of unknowns with the number of equations. It always escapes you, no matter what we've ever tried. And so there was a lot of hope early on that we could actually tackle this by sort of averaging over some of these fluctuations and see where that got us. But in the end, it doesn't really. We haven't got any closer. Still have that closure problem. So, and that's really the problem. Yep.
The surface, as you also talked about solar atmosphere and solar physics.
Yep.
If we look globally, the surface and above the surface, the chromosphere and corona, the temperature varies, densities varies, and in turbulent flow, the inhomogeneities are very short scale. As I have never worked on turbulence, first I tell you, but what I understand is that if in a global picture, we see it is a turbulent flow from surface to the corona, etc. But then the structures, nonlinear structures like coronal holes, coronal lobes, spicules, they are produced at different layers. So turbulent flow gives rise to the ordered structures as well, like at the surface of the sun. On the other hand, we observe what I have done some calculations, that ordered flows or ordered structures can also be produced if we ignore dissipation, etc., and consider the ideal fluid. So how do you relate this?
Okay. So that's a good question. So One ordered flow, one ordered phenomena that I mentioned, I'll get back on Earth, which is the magnetic field, arises from a very complex turbulent flow that must be going on in the core. But that's a very ordered object itself, the magnetic field. Now going to the sun, so you talked about coronal loops and there are the flares and things like this. So I didn't show this, but we also obtained data on solar flares, and we analyzed those data in terms of their statistical properties. And it looks very much like what we measure in our experiment in the sense that there's a certain power law roll-off of the probability density function, which is identical. And that's typical of many complex systems, actually. They sort of has a roll-off of -1. But it goes beyond that. So this turbulent how do flares arise in the first place on the sun? And it's usually when magnetic field lines get close, right? Or try to, they can't really connect. And these are really explosive events. There's some that are really highly explosive, but there's some that are not quite so explosive. And this is because the magnetic footprints, and this is due to this, Parker, the magnetic footprints of these are being moved around by the convective field in the outer core of the sun. Sorry, the outer surface area, and through these convective motions, probably this is what's moving. This is Parker's conjecture, anyways. What's moving these magnetic field lines closer and closer in proximity, which is leading to these explosive events. And in fact, that seems to be, it's actually quite remarkable because statistically it looks very similar to what we see in convection, pure convection, without conducting fluids, et cetera, in terms of the kind of statistics. Sorry, I didn't mention the statistics we're looking at is the flare lifetime, and in the terms of the sun, because they're spread out over many scales. And what we're looking at in turbulence are that there's a mean flow. I showed you a picture, Kadanoff drew a cartoon of plumes getting driven around and around, but that reverses. And so you have these reversals of that, and it goes back and forth in a non-periodic manner. And that time period, which it stays in one direction, also varies over many scales. And so if you look at the probability density function, that has a power law roll-off, which looks identical to the one on the sun if you look at the lifetime of flares. And so we think there's a common, so there's two ways to interpret that. One is that all complex systems have similar roll-offs if you choose the right variable to look at. The other thing is, well, maybe there's actually a much more physical, larger similarity physically in terms of those convective reversals, et cetera, which might bring magnetic field lines together. So at any rate, but yeah,
the creation of structures may be called the self-organization or not?
Yeah, it is. And so even self-organized criticality is we've analyzed everything we've produced also in terms of self-organized criticality models, but that is there are self-organized. So the flow I was just talking about in a convection cell is self-organized. So plumes are just randomly, these plumes of things that are rising in the air all the time are randomly generated, but they self-organize into a large scale flow. And that's, so that is, so the larger scale flows are actually due to self-organization of the smaller scale structures, which are being produced by whatever mechanism you're throwing the heat in, whatever. So yeah, that's absolutely right. A lot of self-organized flows occur, features occur turbulent flows. And, and in fact, the other last thing I was going to mention there was, when we went to low temperatures, we went because we wanted the properties of helium to allow us to explore the far reaches of our Reynolds and Rayleigh numbers. But the other thing is, when you have a model which describes emitting plumes, which are just features of boundary layers being expelled from a hot surface, When that happens in reality, it leaves a hole in the plate, a thermal hole, which has to be filled. So it takes some time for the temperature isotherms to become flat again on your surface. And that's not what the theoretical models are, toy models, the ones I've been talking about, and they don't have that feature in them. And so the models predict one behavior, and the experiments might actually give you another, because the experiment can't keep up with the expected rate of plume production. And when you go to a low temperature environment, because of that vanishing thermal heat capacity, it actually can. It keeps up very well. That's something called the BO effect, and measured by a BO number. But anyway, that's the other advantage. So there are two advantages. One because of the helium, but like the very last thing with diffusivity, or that problem with the plumes, just the low temperature environment is a really wonderfully conducive environment in which to look at these things a little bit more precisely without having those complications. Because in the end, once you start adding corrections on corrections, you get further and further away from what you really wanted to try to understand.
So,
We'll take the final question. It's in the chat by Mr. Osman right at the end.
Does quantum turbulence have possible applications like Kolmogorov turbulence? Well, yeah. So every time we we submit a proposal to study quantum turbulence, I think most of us cite the LHC or the RIC accelerator, Brookhaven, or some other accelerator, which uses superfluid helium to cool magnets. And in fact, if you really want to understand, I mean, really giving you application. If we really want to understand the cooling properties in those for those superconducting magnets, you need to understand a little bit about the turbulence which is happening in a superfluid, because they don't flow normal fluid helium; they're flowing superfluid helium around, and that is it's actually even more complicated. There's phase transitions, etc., vaporization. But at any rate, it's a very complex flow, but it is essentially quantum turbulence, and we really do need to understand that. The other applications probably are in astrophysical phenomena, because there are many which again look very similar. Even going back to the Big Bang with the quark gluon plasmas, you can imagine there are many things that look like superfluid flows that could be turbulent. In fact, the Big Bang had a lot of turbulence, we believe, because you see fossil remnants of that turbulence. Even in the background radiation, you see the sort of patchiness you might expect of a turbulent flow at the beginning. So anyway, I think those applications to systems that look quantum in some sense in nature also are applications of quantum turbulence, whereas Kolmogorov turbulence really applies to everything, most of the things we see, including in stars. I mean, nobody's going to claim, unless it's a neutron star. It's basically it's a classical system. It's just hard to define what the length scales really are, and it's hard to define what diffusion coefficients are for a plasma. But Hamid, you know that better than me.
So thank you very much, Joe. I am really personally grateful to you, and also on behalf of Comstech. I think we must be very grateful to you. You think that you have spent, I think, almost 2 hours here, and we are very happy. And I think it was an exciting lecture. People learned a lot of things from you, and I also. So thank you very much. If you want to say anything or suggest anything, we are happy to know. And everyone, I think, here knows you well. So if you want to ask any question apart from physics or other thing, you are welcome. Even about ICTP, if you want to ask. Because next year, I think there is no activity on plasma physics.
I don't think so.
Yeah.
Check, because it would go through the Atomic Energy Agency in Vienna. I can actually check that. I didn't check it. We actually just got notification 2 days ago of acceptance of all activities. So so some are going on. If they didn't feel like they virtual activity, then maybe they didn't apply. But anyway, I think I'm hoping, I was hoping in 2021 that 2022 would be different, but I can still hope that 2023 will be different. It's just, it's complicated. The nice thing about ICDP is, and it's really Abdus Salam's vision was really to bring everybody. It wasn't just to bring a few people and not just Europeans, or it was bring everybody in the world there. And that's, with COVID, it's hard to do that with all the different regulations and quarantines. And, Europeans can now come pretty easily, but hardly anybody else can. So, it's going to take a bit more time. But I think it's still, ICDP is a wonderfully unique institution. It has a wonderfully unique Pakistani origin. And the last thing I really want to say is I'm really looking forward to returning to Pakistan. I've been interacting with a lot of young people in Pakistan, thanks to Hamid, because you really kind of tuned me to the potential, and demographically, Pakistan's a young country. And I think the scientific structure is there. I think we just have to strengthen everything, and then, we can't do everything. ICDP is a small institution still, but I think there's a lot of things we can do. And I think it's just finding people that want to do that.
Yes.
So anyway, I'm looking forward to coming back.
Okay, so thank you from our side. Thank you very much again.
Oh, thank you.
Bye-bye then.
Okay, we'll see you until we meet again for the ghost.
Yeah, sure. Oh.
Okay, bye-bye.